Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over how to calculate the cell potential under non-standard conditions. So this is practice problem number 2. In previous problem I had two half reactions here, and I showed you how to figure out what the non-standard cell potential is. So here are two other half reactions that were given. So again, we're given these half reactions, oxidation and reduction, and we're asked to find the electrochemical potential of the cell under these non-standard conditions. And the non-standard conditions are here written in the molarity in parentheses. So we have 0.010 molar for VO2 plus ion, and we have a 1 molar solution of H plus. We have 2.0 molar of VO2 minus or 2 plus ion, and we have our nickel 2 plus ion at 2 molar. So these are non-standard conditions, and so we want to know what the cell potential is going to be under these conditions rather than standard conditions, which is 1 molar concentrations. Okay, so the first thing you want to do when you're given the two half reactions is you got to make sure that the electrons in both half reactions are the same. Because remember, if you balance a redox reaction, you separate it out into its two half reactions, you balance the mass, and then you balance the charge with electrons. And then before you add the two halves back together, you need to make sure that the number of electrons in both halves are the same. So that way, when you add them together, the electrons can cancel out. So here we have two electrons being released by our nickel. And for this reaction, we have one electron being taken up here as a reactant. So in order to get these electrons equal, I need to multiply this equation by 2. So this half reaction will need to be multiplied by 2. So we'll multiply 2 times this. The oxidations can stay the same. So I'll rewrite the oxidation. So the oxidation half reaction, and I'm going to write it without the molarities. I'll keep the molarities here, but I'll write it without them here. So this is Ni solid giving rise to Ni2 plus aqueous, and then plus the 2 electrons. And then for the reduction half, we're going to multiply everything by 2. So 2 times this gives us 2 VO2 plus, and this is going to be aqueous. And then we're adding 2H2, but 2 times 2 gives us 4. So this is going to be 4H plus, again, aqueous. And then 2 times 1 gives us 2, so that's going to be 2 electrons. And then that's going to give rise to, so we have 2 times 1 over here is 2, so we're going to have 2 VO2 plus aqueous. And then finally, 2 times 1 over here is going to give us 2 water molecules, 2 H2O liquid. Okay, so now that we have the two half reactions having the same number of electrons, we can go ahead and add these together for our complete reaction happening in the electrochemical cell. So then the 2 electrons here and here are going to cancel out, and so we get Ni solid plus the reactants here. So we have 2 VO2 plus aqueous plus the 4 H plus aqueous, and then that's going to give rise to Ni2 plus aqueous. Plus these two. So it's 2 VO2 plus aqueous plus 2H2O liquid. So now we have our full complete reaction from these two half reactions. So the next thing to do is look up in our reduction table so for the electrode potentials for these two half reactions. So remember, when you're looking up the electrode potentials in your textbook, the table is written so that all the reactions are reduction half reactions. There's no oxidation half reactions. So when you're doing that, keep in mind that they're all the values that are given are for the reduction half reactions. So when you look up this one here, we get, what do we get? That's going to be 1.00. So this one right here, the standard electrode potential for this one is 1.00 volts. That's a positive 1.00. So I'll underline that. And then if we look up nickel as a reduction half reaction, we get the, where is it? Negative 0.23. So here it's going to be equal to negative 0.23. So these are the values that you would find on the table. I haven't changed them. So again, this value is actually for reduction, but here nickel is undergoing oxidation. So this value is not really the value that goes with this particular reaction. So for because this is written in the oxidation form, but this applies to the reduction form in the table. And I'll explain why that's important to keep in mind at the moment. So when you add these two half reactions together to get the full reaction, then what you would do is you would add the actual electrode potentials for these. Since this is written in the oxidation form, not the reduction, you would have to change this to a positive sign and then add them together. So then what you get is the standard cell potential for this reaction here is going to be equal to these two added together. So this plus this. So 1.00 volts plus 0.23 volts, and we get 1.23 volts for our standard potential. Okay, so again, we had to make this a positive because this is the oxidation, but we could keep this as a negative and use this equation here. So this equation requires that we put in the electrode potential given in the table unchanged. So we look up our values, we get the values on the table, so we get this value on the table, and we get this value on the table, and we plug it into the equation as is. So then if we do that, we would get E cell, standard E cell, is equal to the electrode potential at the cathode. So if you don't remember what is happening at each cathode or anode, then remember a red cat and an ox. So red cat, reduction happens at the cathode, and an ox, oxidation happens at the anode. So we have reduction here. This is happening at the cathode. So that means that we would put this in first for this. So 1.00, so 1.00 volts. And then we would subtract out whatever is happening at the anode. Oxidation is happening at the anode. So here we have oxidation, and so that would be a negative 0.23. So we're going to subtract, put the negative there, and we're going to subtract a negative 0.23, 0.23 volts. Oops, I forgot the negative. Negative 0.23 volts. And so a negative times a negative is positive, which is what we got here. So we're going to end up adding those together, and we get 1.23 volts. So same answer. So this is the electrode potential of the cell, the potential, the standard cell potential. So now we can use the Nernst equation. So let's go ahead and calculate Q. So we need to find the reaction quotient. So remember, the reaction quotient expression comes from the law of mass action, where you are looking at the concentrations of products over reactants. So here, and we're going to ignore solids and liquids. So we're looking at this equation in particular. So this is a liquid. We're going to ignore that. Aqueous, 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 solid. So solids and liquids we ignore. So we're going to ignore the nickel solid and the water liquid. So everything else we're going to keep. So it's going to be products over reactants. So we have nickel 2 plus ion multiplied by the next one, which is VO2 plus. And there's a 2 there, so we're going to put a square there. And then we're going to put on the bottom your reactants. So here we have VO2 plus. So we're going to put VO2 plus. On the bottom, we have a 2 there, so that means we're going to have a power of 2 there. And finally, we have our H plus ion, so we're going to multiply by H plus. And we have a 4 as a coefficient, so we're going to have a power of 4 up there. So now all we need to do is plug in the concentrations. So now we're going to come to the concentrations given to us here, 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 and here. So nickel 2 plus concentration is 2 molar. So then that's going to be equal to 2.0. And we're going to multiply that by the concentration of VO2 plus. And so VO2 plus is here. And that's given us here. So 2.0 as well. So 2.0, I want to make sure 2.0. So 2.0 squared. And then underneath that, we got VO2 plus. So VO2 plus has a 0.010 molar. So it's going to be 0.010. And that's squared. And then we have our H plus concentration, 1 molar there. So then it's going to be 1.0 to the 4th power. And when we calculate that, we get, let me double check here. What do we get? Let me calculate that out. And we get, this is equal to 80,000. So 8.00 times 10 to 8 the fifth. Nope, fourth. So this is our Q value. So now we can plug that into our Nernst equation. So let's go ahead and write that out here. So here, I'll start over here. So we have E cell is equal to the standard cell potential, which we calculated here, 1.23. So 1.23 minus, and then it's 0.0592 volts. So 0.0592 volts divided by the number of electrons being transferred. So here we have the number of electrons being transferred is 2. So that's going to be a 2 down here. And that's multiplied by the log of Q. So multiplied by log of Q. And Q we calculated as 8.00 times 10 to the 4, 80,000. So now all we need to do is calculate this out, and we get here, it's going to be 1.23 minus 0.145, 0.145, and that's going to give us, really quickly, 1.23 equals, and that's going to give us 1.084. So we'll just round it to 1.08 volts. And so that is the voltage, or that's our cell potential under these non-standard conditions. And so that is how you solve these types of problems. I hope you enjoyed this video. If you learned from this video, if you got anything out of this video, then please, by all means, like the video, share the video, hit that like button. Also, make sure you subscribe to my channel, hit that notification bell, but when you do, make sure you click all so you'll be notified by all the videos I put out. And also, finally, put a comment down below. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me. Have a great day.